Today, for a new episode on the Dialogues Design Directory, we're going to speak about two very important factors. How do you ascertain the amount of natural light that you need in a building? And at the same time, how do you take measures to control that light so that the heat gain is not taken in, but the natural light is yet taken in? So we'll start by taking a case study example. This is an office building that we recently did a proposal design for, which sits on the main road in Mumbai. And because of the height restriction, we had to create a floor print that was large. And in that large floor print, the lower level houses the lobby. There are 5 upper levels of parking. Then there is a complete refuge floor. And after that, there are 9 levels of offices. Now, looking at how one would typically do it, if this was the building that we were to make, with light penetration from the outside only reaching till about 8 or 9 meters in depth, you would have a whole central portion which would be 50% of the office area without any natural light at all. Therefore, what we did is create a whole cut inside facing the north. So this allows natural light from the northern side to come into the building, and here now the depth has been reduced and natural light penetration is complete in the building. And finally, as a section, this is how it sits. You have parking levels, and then you have an elevated atrium space, either side of which are 2 office blocks that go in and turn and form a C shape, making a central open atrium landscape space. Now let's understand, how do you ascertain the amount of light that is required in a building? So these are the studies that we did based on a software program which analyzes the spatial daylight autonomy of the building, which means that do you get enough natural light into the internal spaces or not. So when we did the first study on the complete pure rectangular block, this is what we found, that the orange portion is which gets natural light and the blue portion is what does not get natural light. So in this case, 50% of the office area would not have any natural light throughout the day, which means it is not energy efficient and you need artificial lighting throughout the day. As compared to this, when we made this cut which faces the north, you get 70% of the office space with natural light and a very small portion in the center which does not have natural light. And this small portion also includes the service areas and locations. So if you holistically look at it, 85% of the office is getting natural light throughout the day at all times when there is light outside. So now we finished studying how you can get more natural light into the building. Once again, it's called spatial daylight autonomy, which means do your spaces have enough light throughout the day. But with the light coming in, there is another factor. In tropical climates, along with the light coming in, there is also heat coming in. So to study that, there is another software called the annual sun exposure. Now in the annual sun exposure, let's look at it. When we did that study on this building, the annual sun exposure, if we were to do the building completely in glass, would have been in the region of 60%, which means 60% of the area on the entire perimeter where there is glass would get in so much heat that your air conditioning cost would go up by as much as 30%. As compared to this, if you were to simply puncture the windows into the facade, so thereby reducing the amount of glass, that entire annual sun exposure goes down to 30%. So from 60% it has gone down to 30%, which means a huge saving in energy and in air conditioning costs. In addition to that, when we start doing fenestration, which is any kind of sun breakers in the building, that further reduces. So once we did the final elevations and we did all the fenestration, the annual sun exposure went down to 18%, which is very marginal. So this is the building as we envisaged it. That's the cut with this elevated atrium where all the offices look into this landscape space. These are sun breakers taken specially to block out the east and the west. And so all of these elements add and contribute towards reducing the annual sun exposure, but at the same time adding to the factor of spatial daylight autonomy. So the ASC goes down and the SDA goes up by virtue of the design, which is including the cutout and narrowing the footprint of the building and making it more exposed to get natural light in, but at the same time sheltering it from direct glare. So that reduces the heat gain and at the same time it reduces the air conditioning cost. So these are very important factors that one requires to do in order to be able to control the amount of light that comes in. You need to have natural light, but at the same time you need to get it in such a way that the light should not get heat along with it, and which is where orientation becomes very important. Now the same study we had also done in the Prestige University, which is now getting complete, where this entire building is stepped. It has a floor plate of 80,000 square feet. When we did the first annual sun exposure study, we found that we were getting about 40% in terms of heat gain on the entire perimeter, because this is situated in Indore, where the climate is very hot for 8 months of the year, in excess of 35 degrees Celsius. So by adding a whole screen on the perimeter, that has been reduced to 14% only, which means there is again a huge air conditioning cost difference. And in this large floor plate, there are a number of courtyards which puncture the building, bringing in indirect natural sunlight all over. So the spatial daylight autonomy is as high as 85%, which means that 85% of the spaces within the building are getting natural light throughout the day, every day. It's really important to study how you can get more light in, but at the same time regulate the amount of light that comes in, because with light in tropical climates you get heat simultaneously. So these studies of the ASE, the annual sun exposure, and the spatial daylight autonomy is very, very important for any kind of building before you start the actual execution.